Testing, testing, 1, 2, 3, testing, testing. Testing, testing, everyone is testing. Testing my patience. Testing. I don't know. That's all I got for testing puns. Maybe we can crowdsource some testing puns. Seems like the latency is pretty bad today. Can I get a latency check here? When I clap my hands, if you could just like put a clap emoji in the chat or something like that. All right. 1, 2, 3. $19 seconds. So about 20 seconds. Cool. You know, that's like washing the hands, not clapping the hands. Right? But whatever. Okay, cool. So about 20 seconds. That's about double what it usually is. Let's see here. Oh, well, yeah. I've been bumped back to normal latency from low latency. I can't fix this on stream, unfortunately. Once the stream has started, I can't bop myself into a better one. So it goes. All right. So, are there any questions, comments, or concerns from anybody in the class? I'd like to see if we can finish hashing today. Okay. All right, so let's get to her. So, last time we were talking about hash tables. Hash tables are a very interesting algorithm. You hear about them quite a lot. The hash table is interesting because it takes something that's logarithmic, that is to say, key-value pair searching, and it turns it into something that, while, not guaranteed, especially if you're using chaining to resolve conflicts or collisions, pardon me, worst case scenario is linear. We're kind of in a quicksort scenario here, except that rather than being proportional to, or rather than being very close to logarithmic time with a very bad worst case, this style of hashing is very close to being constant time with a very bad worst case. And as worst cases go, it's really not that bad at all, because linear isn't that bad, relatively speaking. Although, if you're dealing with 10 gazillion elements, then, it is pretty bad. So, just quickly reviewing hashing. We have an array, right? We are taking the key and computing a hash from the key using the hash function. Basically, the rest of this, the rest of these slides are going to speak about various ways that we can construct a hash function. So the idea is we have a universe of possible keys, and we want to take that and map it onto a much smaller set of hash values, which will be the indices of an array. And since array item lookup is in constant time, looking up anything using a hash table is as simple as computing the hash, using that hash value to index the array, and then, finding whatever you need in the linked list that results therefrom. The idea is that these linked lists will be very small in comparison to the total amount of data going on. So, good. So we were just about to get into what constitutes a good hash function. So, condition number 1. The probability that the hash values of k1 and k2 are equal should be small if k1 is not equal to k2. Obviously, like, your hash function should be repeatable, right? Because if your hash function gives you a different answer every time you call, or every time you feed it k1, then it's, not going to get you to the same address in the array each time, which kind of defeats the entire purpose. But if you have two distinct keys, the probability that their hash values should be distinct should be quite high. A good hash function approximately satisfies the assumption of simple uniform hashing. Each element of the universe of possible keys is equally likely to hash to any of the m slots, independently of where any other elements of the universe of possible keys have hashed to. So, just to drill this down a little bit. So you have your universe of possible keys, right? You have all of your slots that they're hashing into. Simple uniform hashing basically means that if you compute the hash value of any random element of the universe, if you were thinking in terms of a probability distribution, right, you would have a uniform probability that any particular element hashes to any particular slot. That's where the word uniform comes from. Good. So, examples. Let us suppose that the universe of possible keys from 0 to n-1, that we have a universe of keys from 0 to n-1, and that the cardinality of the set of hash slots is m. So there are m hash slots, and all elements of U are uniformly distributed. So that is to say, when we select an element from U randomly, that also is a uniform probability distribution. If we were to write a function to retrieve for us a random element of U, there would be an equal probability that any particular element of U comes up. So, if we consider the following hash function, hash of k is equal to k over n times m, and then you take the floor of that, this approximately satisfies the condition of simple uniform hashing. So, basically, right, you take the key that you're trying to compute the hash of, you divide it by the number of possible elements in the universe, and then you multiply it by the number of hash values that you're trying to fit. And then, of course, you round that down. So, taking, for example, if we have n is equal to 100 and m is equal to 10, then the keys in range 0 to 9 get hashed to slot 0. Keys in the range 10 to 19 get hashed to slot 1, etc., etc. So basically what this is we are dropping, it's kind of like we're doing histogram buckets, right? If the key value is in a particular range, it gets hashed to a particular hash value, and that's sort of going to be evenly distributed among all of the divisions that we're making of the universe. Most hash functions assume that the universe of keys is the same as the natural numbers. This is normally a decent approximation because binary arithmetic, in the end, can be mapped reasonably easily to the natural numbers. It's, I would say, more natural to do that than to map them to the integers, for instance. So, any questions about that? So far, so good, it seems. So in the previous slide, we made a big assumption, right? We assumed, right here, all elements of U are uniformly distributed. This is something that you rarely will actually know, right? Very often, just, almost from sheer size of the thing, you rarely know what the probability distribution is by which elements of the universe of possible keys will be presented to you. In practice, we can often employ heuristic techniques to create a hash function that performs well. Qualitative information about the distribution of keys may be useful in this design process. So, for example, consider a compiler's symbol table in which the keys are character strings representing identifiers in the program. Closely related symbols, such as PT and PTS, often occur in the same program. A good function would minimize such variance to the hash, hashing to the same slot. So, for example, your keys may very well be strings, right? That's actually reasonably common. Your hash function will compute an index from a string by some mysterious means, right? Maybe it just adds up all of the ordinal values of all the characters, and then applies some formula or another to it. The point is, you can get numerical representations of strings. You just have to crunch, you have to think of it like the key, generating the hash value from the key is a destructive process, right? So we're not concerned that the string might be readable afterwards. So, when you're programming, you often have highly related variable names, right? So you can, basically, if we're using this approach from previously, where similar things get hashed to the same point, or into the same slot, then if similarity in variable names will also result in things getting hashed to the same slot, it's more optimal to pick some kind of a hash function that will displace things that have similar names, right? Note that some applications of hash functions might require stronger properties than those which are provided by simple uniform hashing. For instance, if you require that keys are close together, you do not hash them to the same slot, as in the case of linear probing. So, good. Now let's talk about, so we talked about this guy, right? Which is, where's the name of this thing? It's not named. That's okay. So let's talk about the division method. In the division method, we map a key k into one of the slots m by taking the remainder of k divided by m. That is to say, the modulus operator. So our hash value is k mod m. For example, if the hash table size is 12 and the key is 100, then the hash value will be 4. because, you know, you needed an example of how modulus works. So hashing by modulus method, the division method, well, hashing by division method is quite fast. It requires only a single division operation. However, not all choices of m are good. In particular, m should not be a power of 2, which is a little bit ironic considering, you know, all of the multifarious times where we've been obsessed with powers of 2 in this, in this discipline. Finally, we find a particular point where a power of 2 is not the right answer to the not the right answer to the problem. So there's a particular reason for this, of course. The powers of 2, when you perform modulus on a power of 2, let me just show you quite quickly here. So let's imagine we had some 8-bit integer, right? When we take mod 2, right? When we take the modulus of some power of 2, let's do a couple of them, right? So mod 1, well, we don't have to worry about mod 1. Mod 2, mod 4, mod 6, 8, mod 16. There we go. So mod 2 how much is that going to be? It's going to be 0. Because basically what the modulus operator does is it says throw out everything, like, okay. So because we're modding 2 here, every digit here is a power of 2, some power of 2. So mod 2 is going to be 0, except for the first digit, right? The same applies for 4. We're sort of breaking the integer up. This is the part we consider. This is the part we don't. So in binary, that'll be 1, 0, which, of course, is 2, right? So with 8, we do the same thing. That's where we split things. So we've got 0, 1, 0, which is still 2. And 16, we just take this whole thing, which is equal to 10. Right? So the problem, and the reason that this is problematic, you're losing a bunch of complexity here. The thing that you want to keep in mind, the thing that you want to do, is you want to maintain this property of simple uniform hashing, right? What that means is that you want to hash in a manner that preserves the complexity of the number that you're hashing, right? So there's a lot of complexity stored in this portion of the number that we're throwing away each time, right? Rather than just throw that stuff away, if we, all it takes is choosing a table size that isn't a power of 2, and suddenly we require the entire, we require the entire table, or, we require the entire number to compute the hash function. So there we go. Does that make sense? Hopefully that makes some sense. Give me a thumbs up if that makes sense. Yes. If m is equal to 2 to the power of p, then the hash value is just the p lowest order bits of k. Unless we know that all lower order p bit patterns are equally likely, we are better off designing the hash function to depend on all of the bits of the key. Cool. Good. So, a prime number not so close to 2 to the power of p is a good choice. For example, suppose we wish to allocate a hash table with collisions resolving by chaining to hold roughly n equals 2000 character strings, where a character has 8 bits. We don't mind examining an average of 3 elements in an unsuccessful search, and so we allocate the hash table of size m is equal to 701. We could choose m is equal to 701 because it is a prime near 2000 divided by 3, but not near any power of 2. Yes. Treating each key k as an integer, our hash function would then be k mod 701. I'd just like to retroactively fix the grammar in this blue statement here. The sense of this sentence is a prime number which is not at all close to 2 to the power of p is a good choice. Okay, good. So, before we go on, I just wanted to address something from last class. So, at the beginning of last class, I had a, shall we say, a moment of weakness. It was a very stressful week for me last week, and I apparently gave the impression of speaking unkindly about the SAS students in the class. I'd just like to say that was not at all my intention. The SAS students are wonderful people, and they're doing their best, and I admire them for that. The people I was angry with were the people in the SAS testing center, right? The testing center is an office which is run by the university where SAS students go to write tests. And like just all week, I had gotten about 20 emails from them, sent not directly from them, but through various students, claiming that I had not sent them information about my tests that week and the previous week, which I actually had. All they needed to do was check their email, so I was just getting a little bit frustrated with them. And it hadn't helped that I had read another email of that type immediately before, coming on the stream. But I'll try to contain my emotions a little bit more in the future. I just wanna say, if you're an SAS student, I love you to bits. I'm not mad at you in any way, shape, or form. I just have a low tolerance for incompetent bureaucrats, that's all. So I just wanted to put that out there. Because one of my students who was a TA one of my TAs for another class is currently taking this class, and he told me that there was a sort of an impression among the student body that I was slagging off the SAS students or something like that. And I just like to say, if that was the impression, I apologize. That was not my intention. So, good. Yeah, it was not a fun day that particular day because I had heard some things about the manner in which the strike might, like the TA strike might happen, which I guess I'm not yet at liberty to divulge, but we will see as time wears on whether or not, you know, things are going to look good or bad in that respect. But anyway, I'll have more information for you on Wednesday. So, multiplication method. We've talked about the division method. Now let's talk about the multiplication method. The multiplication method for creating hash functions operates in two stages. First, we multiply the key k by a constant a in the range from 0 to 1. And we extract the fraction part k times a, which is equal to ka mod 1. Then we multiply ka mod 1 by m and take the floor. Hence, the hash function is, you take your key, multiply by a, take mod 1, this extracts just the fraction. We then multiply by m and take the floor to slot that into one of our available slots. So you can see that the multiplication method kind of functions as a combination of this method that we were talking about earlier and the division method. So the important and interesting part here is that if you take just the fractional component of a number, the fractional component changes quite widely. It will jump around quite wildly whenever you do anything like multiplication to the number. It's a good approximation of randomness, right? Which is what we're going for here, right? We're going for repeatable but random. So, for example, if we take m is equal to 4, k is equal to 105, and 106, so this is the computation for 105, this is the one for 106, and a is equal to 0.5, then math, 105 computes to 2, and 106 computes to 0. That being said, this is a hash table of size 4, so you have to put, this doesn't look like a huge difference, but you have to put it in context of the table, right? Basically, we have put these two values, if you were to imagine the table as a circle, they would be on opposite sides of the circle, positionally. So it's pretty good. This method is pretty good. An advantage of this method is that the value of m is not critical. For example, making m a power of 2 doesn't matter, really. We typically choose it to be a power of 2, in fact. M is equal to 2 to the power of p for some integer, p, so that we have an implementation of k, h of k, which is easy. That is to say, easy to compute. It's actually very easy to calculate something mod base 2, as given previously. You can do this with bitwise arithmetic as well, which is very, very fast. This method works with any a. It works better with some values than others. Knuth is a famous computer scientist, suggests that a should be approximately equal to the root of 5 minus 1 over 2, which is 0.61803399887. Some reasonably long, slightly irrational number works well in this case because, if it's an irrational number, then you're probably, anytime you're doing anything, you're doing something with most of the bits, right? Good. So, good. Now let's move right along, talk about open addressing. In open addressing, all elements are stored in the hash table itself, so we do not perform chaining. We will study 3 open addressing schemes or techniques. The first one being linear probing. So, let H prime, which maps the universe to 0 through m-1. This is the maps to arrow, by the way. So, H is a function. It maps from the universe of possible keys, maps to the set 0, 1, 2, etc., etc., all the way to n-1. We'll say H prime is some given good hash function called an auxiliary hash function. Oh, I've got a question. Let me pause this and do the question. I understand we want to put an equally likely number of elements into different slots, but in each slot, do we want to have a large number of elements, or should we keep it as few as possible? You want to keep as few elements in each slot as possible, particularly when we're doing collision resolution via chaining. So, you know, in a somewhat smarmy manner, last time in class we said, well, this could be improved if you made each of these, linked lists into something like a binary search tree. But in general, to look something up that only has one to look something up in a hash table and be presented with a linked list containing only one item, that can be processed in constant time. But as soon as the number of elements that your hash table is pointing to, as soon as that becomes proportional in any way to the number of elements that you're storing in the table, you're beginning to introduce, again, a worst case linear runtime. So the whole point is to try to keep as few elements colliding as possible. Collision is something we want to avoid. With cars, as with hash tables, collision is something you wish to avoid, although not at all costs. It's a bit more serious in a car than a hash table. Let's put it that way. But yeah, so in each slot, you want to have as few elements as possible, because it keeps the lengths of the chains short, which means the chains remain highly quickly searchable, which means your whole data structure runs quickly. This is why, like, in general, and contrary to where is it? Where's the thing about prime numbers? Ah, here we are. So contrary to this example here, the ideal case would be that you would have a hash table the size of the number of elements that you want to store in the hash table. The problem, of course, with this is that the hash table cannot be expanded after its point of creation. To expand the hash table would mean requiring the hash function to be able to compute new values, which it previously was not able to compute. This will very likely have the effect of scrambling which data is in which value is associated with which key, right? Especially if you're using something like this guy, which does quite good scrambling, right? So there you go. Keep the number of elements at each slot as low as possible. Try to keep the table relatively big, or, quite large. It needs to be large enough to mostly handle everything that you might want to store in it without using chaining. That's the ideal. Make sense? Hopefully. Good. So, linear probing then. So h prime is a good hash function, sometimes called an auxiliary hash function. Linear probing uses the hash function h at ki is equal to h prime at k plus I mod m, for I is 0, 1, 2, 3, etc., all the way to m minus 1. I is sometimes called the iterative index. So, given a key k, the first slot probed is t at h prime of k. If this is occupied, we probe the next one, t at table at h prime k plus 1. If that is occupied, we probe t at h prime k plus 2, etc., etc. So, I remember last class I asked a question which had a lot of good answers. What do we do in the case of collision on a hash table? And one of your esteemed colleagues said, well, they basically described this algorithm. At the time, I was looking for the linked list version, right? But I just want to show that whoever you were in the chat that suggested going to adjacent unoccupied slots, you were correct, just not correct, you were correct later on. You were describing a more complicated algorithm than I was describing at that time. So, example. Let h of k equal k mod 17, and h of ki equaling h, and like the hash value itself, h prime k plus I mod m. So suppose we wish to store the keys 100, 67, and 66. For k is equal to 100, we have h of k comma 0. That's 100 mod 17 plus 0 mod 13. Therefore, you calculate that out, we get 2. For k equals 67, we have 67 mod 17 plus 0 mod 13, which is 16 plus 0 mod 13, which is 3. So, slot 2 gets 100, slot 3 gets 67. Now for 66. We calculate 66 mod 17 plus 0 mod 13, which is 15 plus 0 mod 13, which is 2. But since it is filled, occupied, we use the next. We use the next I value, so we add 1 here. This results in 3. 3 is also still filled, so we use I equals 2. Plus 2, therefore, that gets 4, therefore 66 goes in slot 4. So we add this one, then we try to add here. This one's free, so we add it there. There we go. Open addressing is easy to implement, but suffers from the primary clustering problem. Long runs of occupied slots build up, increasing the average search time. So, essentially, it's kind of like you're storing the elements in a list, but the list has been collapsed into the table itself. So, like, the size of these continuous blocks of numbers is proportional to how long it takes to search this thing with linear probing. Question: What if every slot is filled? Then the table is full, and no more elements can be added. So the add element operation, I imagine, would fail. Good question. Long runs of occupied slots tend to get longer, and average search times increase. So the problem with linear probing, if you consider a continuous segment of numbers as having, like, you have a certain probability of hitting that, right? And the probability of hitting a continuous set of numbers increases with the size of that continuous set of numbers. So if it's half of the whole table, which is continuous, then you have to search half the table to find a slot that's open. Is it just a coincidence that this is sorted in descending order? Yes, that's a coincidence. It's a coincidence that that is sorted in descending order. Like, for example, if we chose something that was, 17 off of this, or 17 less than this, or if we chose 16, for example, then this would be a 16 here. It's not doing any, sneaky sorting in the background. Good. So, quadratic probing uses a hash function of the form h naught of k plus c1i plus c1i squared mod m, where h is a good auxiliary hash function, c1 and c2 are not 0 and auxiliary constants, and I is, of course, ranging from 0 to m minus 1. The initial probe is t at h of 0, I. Later positions probed are at offsets by an amount that depends in a quadratic manner on the number I. So this solves our problem of clustering, because rather than just going 1 over each time, we are making reasonably large jumps each time, and the size of the jump increases quadratically with the number that we're going with. So if we hit enough, blocked parts, right? Basically, if the value of these two terms, c1 times I and c2 times I squared, if that becomes sufficiently large in comparison to the size of the table itself, then if you're taking if you're taking the modulus of that operation, you're essentially talking about random insertion, or random probing. So, question. What if k equals m and t of m is full? Will it go back to the start? Yes, that's kind of the that's the whole point. That's what mod does, right? So the modulus operation, right? So we can imagine that, let's just imagine the rest of this table was full, right? So we probe here, and we just go, we go. So what would this probe be? The result would be 12, right? Because we're ranging here from 0 to m minus 1. So this would need to come out mod 12. If you add 1 to that, that flips around and turns into 0. So you don't even have to do anything. You don't have to write an if statement for this or anything. If you just add 1 to something that is having mod 13 applied to it, it will end up 13 mod 13 is 0. So it will just pop to 0, and there you go. It'll wrap around automatically to the beginning of the table. Numerically, which is fun. Good. So, let's take the same numbers and apply quadratic probing instead of linear probing. So, let's take C1 is 2, C2 is 3, and let's just do the same numbers, 167 and 66. So, for k is equal to 100, awesome. We have 100 mod 17 plus 0 mod 13, which is 15 mod 13, which is 2. So 100 will hash to the same value that it did before. K67, again, because it does not, because the slot it's hashing to is not occupied, it will again hash to the same slot that it did before, which is slot 3. For 66, it will hash to slot 2, which is occupied, just like it did before. But since it's filled, we now use I equals 1. Because it's filled, we use I equals 1. But in contrast to the last time, instead of just adding 1 to the index, we now add 2 times I plus 3 times I squared, which comes out to 5. So we're actually taking 20 mod 13, which is 7. So rather than hitting this guy and then having to jump to the next one after that, we just pop him into slot 7. Make sense? Hopefully? So, quadratic probing works much better than linear probing, and clustering can be avoided. However, if two keys have the same initial probe position, then their probe sequences are the same. If each slot can only hold one element, why don't we just use an array? Why don't we just use an array? So, we're trying to remove the bias in the universe, right? I know that's like, you know, I know we live in this postmodern age where it is claimed that everybody and everything is inextricably biased by a person's subjective experience of the universe. However, in math world, we still think that bias is bad and that we should try to remove bias. So the point of the hash function, right? Because basically now we're just talking about the hash function, right? We're talking about an array in which we've left a bunch of blank space plus a hash function. The purpose of the hash function is to randomize the position that a key would take in the array, so that it's, you know, so that we have a minimized possibility of collision. That's number one. That's the first problem. And the other problem is, remember we have this issue that the universe of possible keys might be much larger than what you might want to store in that array, right? So if we imagine the universe of possible keys to be something like, you know, standard-sized integers, 32-bit integers, right? You're not going to declare one slot in memory for each possible integer value, right? There's a very large number of them. I think there's like 62 billion or something like that, which is, you know, a lot of memory to consume for just one table. The idea is that the size of the table is much smaller than the size of the universe of possible keys, right? So this is a way also of crunching down all of the possible keys that you have to a manageable size and still being able to access them in constant time. So there you go. And by the way, there's nothing saying these couldn't be structs, right? This could be an array of structures. So despite the fact that they're claiming that this is, just a single element in here, it doesn't necessarily have to be. Good. So, where were we? Quadratic probing. Problems with quadratic probing. So, one problem with quadratic probing: if two keys have the same initial probe position, then their probe sequences will be the same. Since h at k1, 0 equaling h at k2, 0, that implies that h of k1 at I is equal to h at k1, k2 at I, by inductive argument. This problem leads to a similar form of clustering known as secondary clustering. So it's not as bad. It's not as bad as primary clustering, because a thing won't just cluster against a whole bunch of things that it doesn't even, that are unrelated to it. In this case, only things which hash to the same initial value will cluster. Right? Secondary clustering. So, we're going to talk about double hashing. But we're going to talk about double hashing next time in class, because it is now 9:20. I didn't quite get through hash tables. I don't know, it's a lot of, very dense mathy stuff, but I don't know. Yeah. Any questions? I'm very excited to be done with hashing, because then we get to move on to graphs, and graph algorithms are like so fun. May I ask a question about red-black trees? Sure, ask a question about red-black trees. I'll just pull up the slides. Oh, no, no. No, there we go. All right. I'll just pull up the slides. Could I please draw an example of an RB tree which was height 2 times log base 2n? I won't draw one if I can find one in the slides. So, when we say height, we need to say maximum height, right? This one has a max height of that. So the 2 times log base 2n case comes out when you have one or more branches, which is like a perfect alternation between black and red branches, right? So if we count up the number here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So, you know, let me just pull up Google Calculator. 11, so log base 2 of 11. So, yep. So there we go. That's log base 2 of 11. Of course, you know, 2 times that. That's interesting. So where is that even coming from? I'm gonna have to run to my next class very soon. Oh, yeah, it's the upper bound. You can have one that's no worse than that. Right. So, yeah, the height is 4, but the 2 times log base 2n, that's the upper bound of the height. That's the upper bound of the height. And actually, now that I think about it, you can get, like, that one's not the worst case. You can have, you could have, like, red, black, red, black, red, or something like that. You can have, like, red start here, and then you have, like, you know, one additional red link, but yeah, it's an upper bound, right? So, I don't have one that, like, hits the theoretical upper bound that I can think of, but yeah, I gotta run to my next class. Thank you for the thank you for the fun, thank you for the laughs, thank you for the tears. I'll see you folks on Wednesday.